We proceed our journey with the unitary case. We have just seen that solving Q0 lambda is very easy. The next natural step to take is to ask, what about P0 epsilon? How should this version of the problem be solved? Without dwelling too long on this, it is easy to convince yourself that the very same steps taken for Q0 lambda apply here. The outcome is again a hard thresholding on the entries of the vector z, being A transpose times B. However, this time the threshold is different, and it should be set such that it is the maximal value that meets the epsilon constraint. Strangely, what we have just found is that the good old thresholding algorithm is in fact the exact solver of P0 epsilon for the unitary case. I remind you that in the discussion on greedy methods, the thresholding stood at the very bottom of our list in terms of accuracy, and here we find that it is ideal. What about the other greedy methods? Well, without proving this, we do claim that all these algorithms are as accurate, leading to the ideal solution. Of course, if you can choose, go for the thresholding since it is the simplest. We turn now to the basis pursuit in the Lagrangian form and aim to find its solution. I remind you that this task is not NP-hard, and in fact it is a convex problem. Still, it will be great to discover that solving it is easily obtained with a closed form expression. Taking the same steps as before, it is easy to see that Q1 lambda is equivalent to this simplified form where z is A transpose times B. Again, this is a separable problem of M1D optimizations. They are very similar to what we got before, with only one difference. Instead of having a power of 0 in the first term, we have the absolute values of xk's. And as we are about to see, this difference complicates things a bit, but we will manage this just as well. So how can we solve these 1D problems? The elegant way to go about it is to use the notion of subgradients in optimization, but I will try to avoid this and suggest an alternative derivation. First, observe that the problem is symmetric, and thus we can restrict our study for non-negative z values. We shall further assume that when z is non-negative, so is the solution x, because getting a negative value for a solution makes no sense. Okay then, the solution could be 0 and then the penalty is 0.5 times z squared. If the solution is non-zero, then the penalty is this quadratic expression. And clearly, it is not as obvious as before that we should choose x to be equal to z. So what should x be in this case? Let's choose it so as to minimize the penalty. Little bit of algebra, and we get that the optimal value of x should be z minus lambda, getting a penalty value which has no x appearances in it anymore. Note that the outcome z minus lambda implies that this is relevant only when z is bigger than lambda, since otherwise x becomes negative, contradicting our earlier assumption. We'll proceed now in the same way to the path we have taken with the Q0 lambda, in which we compare the two penalties and choose the smaller one. Comparing the two penalties we got, we see that choosing x to be z minus lambda is always best. So obviously, when z is above lambda, this is the solution to choose. However, for z below lambda, we already said that we cannot choose this solution. In this case, x equals 0 is the optimal value, resulting with the minimal penalty. This leads to this final solution. Here we have exploited the symmetry in proposing the solution for negative z values. We conclude that the optimal solution of the 1D problem we have posed is this curve, known as soft thresholding. It should be applied element-wise on the entries of the vector z. What about P1 epsilon? The answer is very similar to the one we have given for the migration from Q0 lambda to P0 epsilon. The same curve applies, but the threshold is computed differently. So our finding for Q1 lambda is the following. This problem is solved by computing the vector z, being A transpose times B. Then we pass this vector through the soft thresholding curve. The outcome is the globally optimal solution of our problem. We summarize this part that dealt with the unitary case. All the solutions we have developed share the same form in which we compute A transpose B and pass the outcome through a thresholding operation, be it soft or hard. And that's it. This way, we get the best possible solution, even if the problem was non-convex. This elegant solution is a source of envy. Could we borrow it for handling the more general case in which A is no longer unitary nor square? This is our next topic.